All right, we're going to see if we can't wrap up this stuff with angles at intersections and planes and all this other stuff dealing with vectors. All right, so the first thing we're going to look at is a little bit more with angles. In the last video, we talked about how to get the angle between two lines, right? Between two vectors, essentially. And we were able to do that by finding the dot product. Okay, what about if it's a line and a plane? Okay, well, if we want to find the angle between a line and a plane, okay, so we got this plane and we've got some line going through it at a point like this. If we want to find the angle between the line and the plane, most of the time the easiest way to do that is actually to find the angle between the normal and that line, because then you can use the same thing, the dot product. You can find that and then subtract it from 90. Now the other option is, instead of using cosine, you can use sine, because that essentially has the same effect as subtracting from 90. Okay, so very easy. Just use the direction of the line, direction of the normal vector, and then you can find that angle and subtract from 90 to get the angle between there and the plane, because we know it's 90 degrees. All right, but what if I have two planes that are crossing? All right, so I've got a plane going this way and then some type of plane going through this way that you know, intersects and then goes back behind like that. Okay, well, hopefully you can tell that they intersect at a line, which is kind of cool, but that's not what we're interested in. We're interested in this angle here. Now that angle, interestingly enough, is exactly the same as the angle between their two normal vectors. Okay, so in the case of two planes, if I want to find the angle between them, I actually just find the angle between the normal vectors, and that's going to be exactly the same, which is kind of cool. So let's go ahead and see if we can work through an example of that. Okay, we are going to try to find the angle between two planes. Okay, so we've got plane 1, which is in Cartesian form. And you've got plane 2, which is in the unit vector form for a vector. So plane 1, easily enough, we can get the normal vector just by taking, remember, the coefficients here. So it's just 2, -1, and 1. So that was easy. Now the second one's going to be a little bit harder, but if you can recognize that what's going on here is just that we have the different pieces of your vector equation. So let's just look at that. So I've got r equals, and we've got a starting point, which is going to be 1, 2, 0. So 1, 2, 0, because those are the constants in here. And then we've got plus your vector times alpha, and then plus your vector times beta, right? And so alpha is your first parameter, which has a -1 for the x, and then it has a -3 there for the y, and then it doesn't have anything, so a 0 there for the k. And then the beta has a 1 for the x, it doesn't have anything for the y, and then for the z, it's got a 2 beta. All right, so at this point we now have our vector equation. Now, if you remember, this is built up of a starting point, some vector, and then a different vector that's not collinear, that's going in a different direction, that helps then to define your plane, whether it's this way or up and down or whatever else. Now, in order to find, both of these vectors then lie in the plane. So if I want the perpendicular to that, then all I need to do is find the cross product, because the cross product gives me the vector that is perpendicular. All right, so what I'm going to do is I'm actually just going to do the cross product of -1, -3, 0 crossed with 1, 0, 2. And so that will give me the proper vector. And so I'm going to use the formula, which is in your book. So I'm going to go -3 times 2 minus 0 times 0, right? So that is u2 v3 minus u3 v2, and so on and so forth. You can have your formula in front of you. So it'll be 0 times 1 minus 2 times -1, and then it will be negative 1 times 0 minus 1 times negative 3. Okay, and if you need help on that, you probably just want to look at the vector video, which gives us negative 6, 0 plus 2, so that will give us 2, and then 0 plus 3, which will be 3. So I now have a direction vector for the normal, right? Because the cross product will give me a vector that is normal to the plane. And so now that I have the two normal vectors, I can now find the angle, because I can just say this one is u. So the magnitude of n1 is 4 plus 1 plus 1, 5, 6, so the square root of 6. The magnitude of this one, if we call this number 2, the magnitude would be 36 plus 4, which is 40, plus 9, so 49. And so we can now put the two together and solve. So we're going to do the dot product, 2, negative 1, 1. Dot product, negative 6, 2, 3. And that needs to be equal to square root of 6, square root of 49, cosine theta. And so using my fancy schmancy calculator again, I do need to do the dot product first. So that'll be negative 12 plus negative 2 plus 3. So negative 14 plus 3 is negative 11, divided by root 6 root 49 cosine equals cosine theta. So fancy schmancy calculator, we'll go 11 divided by, I guess I need to do 6 times 49, because I actually don't know what that is. 6 times 49 equals 294. So that's 294 on the bottom. So now fancy schmancy calculator, 11 divided by 294 square root equals, and then we can do the inverse cosine, which gives me 129 degrees. 129.9, which gives us the angle between the two normal. Now note that any two lines, when they cross, they're going to give us two angles, this one and that one. Whenever it asks for an angle, whether it's an angle between two lines or an angle between two vectors, we're actually looking for the acute angle. So what we're going to do is we're actually just going to take 180 and subtract this, which ends up giving us 50.1 degrees. And so that's our answer right there. So the angle between these two planes is 50.1 degrees. Now, I don't know about you, but I don't know how I would do all this stuff without vectors. Without all this stuff, it's just way too complicated to think of the actual directions of the vectors and how am I going to get the angle. And I mean, this is pretty cool stuff. I mean, this is cool. Now, I bet you think you're pretty cool sitting there and doing this now. But I mean, I'm sitting here doing this on like a weekend night, so that makes me pretty cool too, right? Yeah? Okay, so we're pretty cool now. Now, I just want to kind of wrap up. There's just one other, I guess two other ideas I want to talk about real quick. Okay, we've already talked about intersections of lines. Okay. So intersections of two lines. We did an example of that, if you'll remember. So we set x, y, and z equal, we solve, and essentially you put the two equations in each other and solve for it. You should always check, because it's possible that the lines could be skew, right? So if you're looking at two lines, they might actually cross, or there might be some space in between the lines so that they don't actually physically cross. So two lines could possibly be what we call skew, which means that they're not parallel because they're not going in exactly the same direction, but they don't intersect, and so we call that skew. All right? Now, we could also do an intersection of a line and a plane, which we already did. Remember, we put the line into its parametric equation, and then we plugged that into the equation for the plane, and that allowed us to solve for the point where they crossed. If you wanted to find the intersection of two planes, that's another interesting problem, because we then need to consider a couple of different things. So let's go ahead and look at that. Let's consider the plane 2x minus y plus z equals 1, and x plus 2y minus z equals 0. All right, so the first thing that we're going to do is we're going to try to put these two equations together and eliminate z. So I'm going to just go x plus 2y minus z equals 0. I add them together. I get 3x plus y equals 0, and I'm going to solve for x. So I'm going to subtract the y and divide by 3, so x equals negative y over 3. Okay, now I'm going to do a similar thing, but this time I'm going to eliminate y. So what I'm going to do is I'm going to take the first equation and multiply it by 2. So that'll give me 4x minus 2y plus 2z equals 2. When I add them together, I'll get 5x plus z equals 2. Again, I'm going to solve for x, so I'm going to subtract z. So I'm going to have x equals 2 minus z over 5. And so now I've got the x values for both of them. And so essentially at this point, so now I essentially have an equation for a line, because I can put into, I wanted to do that again. I can put it into that Cartesian format, right, with the three pieces. And so that's what I'll do. I'll just put this all into that Cartesian format. So I'll go x minus 0 over 1, which is then equal to, you know what, I made a mistake here. That should have been a 1, huh? Oh, schmack. So then it's 1 minus y. So this will be y minus 1 over negative 3, which is then x is also equal to, and then I can go z minus 2 over negative 5. And that right there is the equation for a line. And that is the line where these two planes intersect. All right? I feel that maybe I need to clarify. This is two planes that we're intersecting. Sorry. I feel like maybe I need to clarify on the lines. Just kind of thinking back on this, and then we'll close this video off. What I want to do is find the intersection of two lines, and the way to do that is you write them both in their parameters, right? And so you write it as x equals, for example, 2 plus 3 lambda. And you do the same thing for y and for z. And if you do that for both equations, x equals 1 minus 3 lambda, then you can set the two parameters equal and solve for lambda. If the lambda is the same for all three pieces, then that means that essentially you've done it correctly, and that there is an actual intersection of the two lines. If you get conflicting lambdas, that means that it's skew. And if you find that the two lines are the same, then obviously they're parallel. Okay? So at this point, I'm going to go ahead and end this video, and I'm going to make one last one, which will kind of wrap up the rest of the ideas from this unit.